Okay, let's continue. We done the counters, and now we do something simpler than counter, register. Okay, and then we do Verilog description for counters and registers. Well, we have said this before. Register, all it means is that the control signals of the flip-flops are tied together, and that forms a register. Here is a 4-bit register with parallel load input, parallel load output. See, actually, this is where the terminology parallel loading comes from. When you have 4 flip-flop, these are being loaded in parallel. That's why you have PI0, PI1, PI2. And then that's the same concept used in the counters. Actually, a counter, when it functions like a... when it functions in the load mode, it is actually functioning just like a register. So you can take a counter and not ever make it count up, and then becomes a register. Okay, so register is a simpler form. 4 outputs, 4 inputs, control inputs. Remember also I said that any control signal you have, for example, you have if you have a this is a reset. If you have a set, if you have an active set, active low set, active wide set, all tied together. Any control signal you have for the flip-flops are tied together. And then you have these 4 inputs and 4 outputs. Okay, 1, 2, 3, 4. As soon as clock ticks, you load the input into the output. So this is not very different from a single flip-flop, meaning that if I were to describe this, you have seen that before. Always on pulse edge of clock, pulse edge of reset, and then the D input gets clocked into the Q. And then the same thing over here for Verilog description of an 8-bit register with remember I just said that if you have other control inputs, the control inputs will also be tied together. And if we had an enable input, let's say an enable input for each of these flip-flops, those would also be tied together. That becomes the enable input. And again, enable enables the clock, and therefore the enable, more clear coloring here, enable, okay, EN2, and then 2 sitting next to clock. EN2 means this is the signal controlling the clock, means that if this is 0, clocking is disabled. EN2. Okay, this is my enable input. That ties to all the other enables. Okay. So a flip-flop formed as such. I'm not saying necessarily that the flip-flops have internal enable. And remember, we said that if they do not have internal enable, you can create that using a multiplexer. But the register formed as such looks like this. Okay. 8 parallel inputs. This is 4, just to make it smaller. And then you have 8 parallel outputs. You have an asynchronous reset. This is EN2, 2C1, and this is R. Okay. This is asynchronous, and the clock is rising edge, and then you have an enable. Let's describe this. Okay. First of all, since you have 8 of them, instead of saying my input is D only, now you say 7:0. So that becomes your input. That becomes your input, 8-bit input. Then you have the enable, you have the clock, you have the reset. These are all single bit. And then you declare them just by one input keyword and then continue. Okay, again, nothing different from the regular usual flip-flop. The output, remember we declared our output qreg because we are setting it inside an always the statement. We do the same here, except that my parallel output has 8 bits. Now, my recommendation was when you're doing the description for flip-flops, even though you can do gate, you can do assign, but the most usual that everyone uses is always the statement. And always the statement can become a sequential always the statement. I don't mean a procedure, I mean a sequential. A sequential always statement is one that has the edge of the clock on its sensitivity list. The edge of the clock on its sensitivity list means that pause edge clock. Okay, either pause edge or negate. As soon as you put pause edge clock, this always statement becomes an always statement for a register, a flip-flop, a counter, a shift register. This becomes a sequential block. Okay, for describing a sequential, the memory part of a circuit. You cannot mix pause edge of the clock and a signal coming from somewhere else. Let's say a signal coming like the A input is changing. You don't mix those. The only thing you can mix in the always statement, in the sensitivity list of the always statement, the only thing you can put on the sensitivity list other than the clock are, listen to this, asynchronous controls of the flip-flop. Asynchronous controls of the flip-flop. Okay? Async. Since I do have an async reset, and therefore I do put that in there. With all the limitations and all that, I do have an async synchronous reset, and therefore I put it there, and I'm not worried about that. What else participates in this register? Enable participates in this, but see, enable is not asynchronous, it's synchronous, and therefore I don't put it up there. Even the reset, if the reset was synchronous reset, I wouldn't put it up there. Okay? That's the limitation. And when you're putting something in there, it has to be either pause edge or neg edge. Even if this is the clock is always pause edge or neg edge. Even if it's reset, and the reset is causing the flip-flop to become 0, even that this is not the edge of the reset that causes the flip-flop to become 0, but still you put pause edge reset. And the way we read it is like this. Always on the positive edge of the clock and when reset becomes 1. Now follow the next statement. It says, look, let me read it and then I follow into the next statement. I start with line 3, move into line 4. Always on the positive edge of the clock and when reset becomes 1, I'm in line 4 now. And when reset becomes 1, then parallel output becomes 8 tick decimal 0. Okay? So it's decimal 0 extended to 8 bits. Else means that the reset is not active. What is active then? The clock is active. Okay? If the reset is not active, I'm looking at the clock. the clock is active, but there is a condition that we put on the clock, and that was the enable. So we say, if enable is 1, then parallel output, parallel input goes on the parallel output. Otherwise, if enable is not 1, put parallel output back into itself. That means forget it. The clock arrived, but enable didn't allow the parallel output to go to change, or parallel input to go into the parallel output, and therefore I keep it unchanged. Okay, and actually this statement on line 7 is so much implying this. This is the D inputs, this is the Q output, or parallel out. Parallel out, if enable is 0, is going back. If not, pair in, pair out. Okay, so this statement and this diagram do correspond. Okay, so that's a description for the register. So what I am trying to show here is that the going from the description of a flip-flop to description of a register. You use an always statement. You use the clock edge and asynchronous on the sensitivity of the always statement, and then all the conditions that cause the loading of data, resetting the data, zeroing the data maybe, or zeroing other than resetting, or even incrementing. All the conditions go inside the always statement. If you have an asynchronous control like this one that I have here, if you have an asynchronous control that that is controlling the resetting, for example, that comes first, and then everything else comes after that. Meaning that right now you are seeing that after the else, I am checking for other conditions and perhaps for loading the register. What I'm leading into is if I have a counter, then what do I do? Well, if you have a counter, the place I said red, okay, which is the area where reset is not active, and then you're doing something with the internal register. In this red area, you would put, if count is 1, count enable is 1, carry in is 1, count. Okay? And then all the conditions, whatever conditions you have, goes in place of this red stuff here. So let's look at counter, that same counter that we did before. Okay? Remember the counter. That's how it was. Clock, reset, parallel load. Okay, a load control, a carry in control, a count control, and a carry out. Okay, and then we said that if load is 1, I'm showing the diagram first. If load is 1, then these inputs go into these outputs. If load is 0, carry in is 1, count enable is 1, okay, if load is 0, carry in is 1, count is 1, okay, on the clock, these 4 inputs get added to 1 and go on those outputs. So these 4 inputs, that's the +1 we were showing, go on the output. Let's write the Verilog description of it. first, let's start with the clock and reset. The clock and reset, I have positive edge of the clock and asynchronous active high reset. And therefore, I describe those this area. I describe it by this and this. And if reset is active, I'm putting 4 tick D0, 4 tick decimal 0. Yeah, it is a mistake, but it doesn't matter because Verilog says, well, you're oh, this is a 4-bit. That's okay. I thought this was an 8-bit. That's okay. So even if it was 8, the 4 would be extended to 8-bit. So don't worry about that. All right. So the green area is this green area here. Then I have the loading. Okay. I say else. Remember, here I also had an else. So this was the green area, the clock. Okay, which is this area. Everything is green here. But anyway, this area. And then you have an else. The else here was simple. Just put the data into the register. Here, the else says, well, not that easy. Okay, you have to look at the load. If load is 1, then do the loading. If load is not 1, similar to the enable here, if load is not 1, then consider incrementing. Okay, so what I do here is I'm going to use orange for loading. I'm going to use highlighter or orange for loading. So if load is 1, this is what is happening. See, these inputs pass through to the output or clock into the output. And this is if load is 1, okay, parallel in goes into parallel out, which is what I'm showing here in green, in orange. If I come in here, this if then else has passed the reset, has passed the loading. So loading is not 1, is 0. Now I'm considering counting. Okay? And therefore, this is where I'll be in this case. Else, that means consider counting. If count is 1, if count is 1, okay? If count is 1, then also if carry in is 1, remember I said that you need both ones here. If carry in is 1, then your parallel output becomes parallel output plus 1. Otherwise, what? Otherwise, nothing happens. Parallel out goes into parallel out. That means it's not reset, it's not loaded, count enable is 0, or carry in is 0. In any case, you are not changing the contents of the counter, and therefore parallel out goes back into parallel out. And this is a counter. So what I'm really showing here is that once you learn the Verilog description of a single flip-flop, that's it. Everything else, just more and more conditions, maybe more case statements and all of that, but then nothing major. Okay? And there's one more thing I'm doing here, and now that we are using all kinds of colors, I'm showing you carry out. Carry out is the signal that becomes 1 if you are in the mode, in the count mode. That means CNT is 1, carry in is 1, and all bits are 1. Your carry out becomes 1, and this is exactly what we are doing here. Carry out is 1 if count is 1, and you are doing AND reduction, a very useful construct, and reduction of the parallel outputs and the carry in. That means put all these together. There are 4 of the parallel outputs. There is 1 bit of the carry in. That's 5. And them together, you get a 1 bit ANDing. And then, but then, if count is 1, that means also and count with that. And then if all of these are 1, then carry out becomes 1, and carry out is this. Okay, is this. Lost it. Okay. Otherwise, carry out is 0. Notice that I'm doing the carry out as an assigned statement. You are seeing that my carry out here does not have reg because I'm using an assigned statement. This is an up counter. This is the Verilog description of that up counter. The reason we didn't do the counter Verilog description first, I wanted to wait until we see the smaller one, the register, which is a little bit more, is simpler than counter, and then go from there. See, all that happened from the register to the counter is this area, this red area that I'm showing. Okay, this red area that I'm showing here. See, the else is replaced with this red area. So the frame is basically the same. And then the begin is for putting more and more and more conditions. Okay. This is after the else, and this is after the else. All right, that's the up counter. So what do we do with this? Let's examine it. Does it work? Okay. I'm going to develop a test bench for it, and there are things to be said about the test bench as well. In the middle, I am instantiating this, but then remember, for test bench, everything that you want to give a value to should be declared as reg. So I want to give a value to the parallel input. I want to give a value to the clock. I want to give a value to the reset because I want to test it, right? I want to give a value to load so that I can load it. And I want to give a value to the clock, reset, the count enable. All these I'm giving values to, and therefore they are reg. They are the inputs of the counter. 1, 2, 3, 4. 1, 5. Okay. All of this. 1, 2, 3, 4, 5, 6. 3, 4, 5. Oh. Yeah, I don't know what I is doing there. That was probably left from some other code this was pasted from. Okay. These are the 6 inputs. What are the outputs? The outputs are wire, and those are these. And I'm doing connection by name or name the connection. Okay, name the port connection. I'm sorry, I'm doing ordered port connection, means that everything connects to the component I'm instantiating according to the order that the ports are the ports appear on the port list of the component that is being instantiated. So look here, see, PI comes first. Those are the blue ones. This has exact according the exact ordering as this blue area, and then this is the output ordering, which is this. Which is according to this. Okay. So this is instantiated. Those are declaration of the inputs and the outputs. Inputs reg, outputs wire. Now what I do is I create a free running clock. Free running clock. For that, I use an always statement. Up here, I have set my clock to 0. So my clock is starting at 0. I come into this always statement. There is no sensitivity, so nobody stops it. It waits in there, but then there is somebody stopping it, and that's the 5 nanosecond delay. It delays for 5 nanoseconds, takes the current value of clock, which is 0, complements it, makes it a 1, and the clock becomes 1. The always statement ends. But when the always statement ends, it comes back to the beginning of it, on and on and on forever. Okay, and therefore, initially it starts with 0, then 5 nanoseconds later it becomes 1, it becomes 0, it becomes 1, it becomes 0. It continues until the time that somebody says stop it. Okay, concurrent with this, I have an initial statement. This is concurrent with the initial statement below. Initial statement below starts with reset of 0. Notice again, reset is 0. And then reset is 0. But then wait 7 nanoseconds, set reset to 1. 7 nanoseconds after that, set reset to 0. Okay. Remember, reset is asynchronous, doesn't need the clock, so resets it. And then 13 nanoseconds after that, load becomes 1, carry in becomes 1, 29 nanoseconds load, just trying different things. And the parallel input is all zeros on line 2. And so what you see here, exercising the counter with, or playing with the counter, with the load input, with the carry in, with the count, and all that. And all that happens is, notice initially my parallel output is the red line, that means is X, but then after the duration of X, it becomes 0. That means the, because why is that? Yeah, that's 5 nanoseconds because clock ticks. Okay, clock goes from 0 to 1. Clock goes from 0. Notice that this is the 5 nanosecond. The clock goes up, and that causes the parallel input, which I have declared it on line 2 as 0. That clocks into my parallel output, and therefore you are seeing the X value, which is in red, of parallel output becomes 0 at 5 nanoseconds. This continues 0 until the time that I am doing a parallel loading on line, see on the left hand side, load. Okay, I can't draw when I'm zooming, so this is load. So load becomes 1, doing a parallel loading on the rising edge of the clock. But the problem with that is the counter already has 0. The parallel input is also 0, and therefore you don't see the parallel loading happening. But that's okay. Later on, my carry in becomes 1. That is the signal right above the or count enable becomes 1. That's the signal right above the load, and therefore my counter is counting 1, 2, 3, 4, and then okay, and then later carry in, the line right above the parallel output becomes 0, and no more counting will happen. This is it, and then I have the last statement on line 26. That's a stop. Stop means that do this, do this, do this. There's someone there that is running forever, and unless that person is stopped, that person can take the simulation go on forever. And therefore, you put this stop here, If you have other concurrent statements like the always or as many always as you want, you can have, but then one stop in one initial statement will stop everything. And so after all of this, you wait 100 nanoseconds and stop. And this is the simulation report. Okay, we are done with the counter. We are done with the Verilog description of the counter.